So you're gonna raise everything to the 1/5 power, yeah, negative 9.712%. Are you okay with that?
Yep.
Heidi, you okay with that? Okay. All right. And you can try the other one. So we talked about that, this is just for the video, so since the 1.8% is already a monthly interest, we do not divide this by 12 again. To do that, we would have had 1.8% annual interest compounded monthly, but this is already a monthly interest. Okay, let me give you one kind of like that. Suppose we have, they call hyperinflation when inflation just gets ridiculously big. You see it sometimes in countries that have wars going on and stuff like that, Yemen and Bolivia and places like that. So suppose we had we'll say in Yemen, because I don't know, that's a country that's in a tough situation now. Inflation, we will say, is, let's see if I can get this right, 0.73% daily rate. I think that'll work. Okay, so now that's a daily rate of inflation. Can you find the annual rate of inflation? Does that make sense? So this is similar to the one we just did. I'm not telling you that this is the annual rate and compounded daily. I'm telling you this is already a daily rate of inflation. What does that mean over the course of a full year? Okay, so you can come to the board and do that. So this is an example like the one we did where this is now a daily interest rate or daily percent increase. So we don't have to divide it by 365. It's not annual. That already is the daily percent increase. So if we change it to a decimal and raise it to the 365 and set it equal to 1 plus R, then you're going to get ridiculous inflation rate. So that's like in a country that's falling apart. Okay, now we can rest our calculators. See if you can do this one at the board. So we're writing the corresponding exponential. I write both sides as powers of 2. Once you get power equal to power with the same base, we can drop the bases. We should get to 2/3. We'll try another one. So we're going to write the corresponding exponential. Then to solve for x, we want to raise both sides to the reciprocal power. So when you raise a power to a power, we multiply those. They cancel, just give us 1. So we have x to the first. Now, how you do this, I would think of this first as the 1/9 is 1 over 3 squared. 1 over 3 squared we can write as 3 to the negative 2. Now we can multiply these exponents. The negatives will cancel, the 2's will cancel. We'll just get 3 to the 3rd, which is 27. Okay, so those were good warm-up problems. Now let's do something that's really challenging. Okay, so let's do the logarithm base 2 of the logarithm base 3 of x is equal to 2. So we are going to say, starting with the outside logarithm, 2 to the second is going to be the log base 3 of x. And 2 squared is 4, so we get 4 is log base 3 of x. Then we just do it again. 3 to the 4th is x, and we know that 4 3's multiply to be 81. Okay, let's do another one. Let's do 7 to the 2 plus log base 7 of 2. 2 raised to the log 2, 7 raised to the 2 plus log base 7 on 2.
Yeah, so is the log part of that? Yeah, like in a heartbeat. Yeah.
Yep.
Oh my god.
So we can write that as 7 squared times 7 to the log base 7 of 2. And we know 7 squared is 49, and hopefully we know that the logarithm of 7 raised to an exponential base 7 raised to a logarithm base 7 are inverses. They're going to cancel each other out, and you'll just be left with the 2. And then that's going to be 98, which is our answer.
That's pretty cool.
That was pretty fun. All right. You can take your seats, and let's actually take questions on homework, I guess, first. Are there any questions on homework? Ones you would like to see explained? No?
Oh, I was just wondering why on number 15, taking the log and then just like common log of 10 to the 0 equals 0. But I guess I understand it now. So never mind.
So I think it's worth talking about a little bit, because there's a couple ways you can conceptualize it that are correct. It's okay to say that if a logarithm base 10 and an exponential base 10, they're inverses, they're going to cancel each other out and just leave you with the 0. You could also say, I don't know, so I'm going to set it equal to x. Then write the corresponding, get out of the logarithm by writing the corresponding exponential. And since the base of the logarithm is 10 raised to the x, would be 10 to the 0, and you can see that the x must be 0, and the x is what that whole thing was equal to. That's kind of another strategy for getting to that. One we want to get to is we know that 10 to the 0 is 1. And one of those things that we would like to eventually just know as one of the facts of logarithms is a logarithm of any base of 1 is 0. Because it doesn't really matter what the base is. B to what power is 1. It has to be 0. So it doesn't really matter what the base is. The log of 1 is 0. Okay? Other questions? Okay? Make sure you got a calculator, because we're going to use our calculators today. We're going to solve exponential and logarithmic equations. This is more 5.1. Solve exponential and logarithmic equations. So this will give us an alternative to solving some of those that we have in the last chapter, or up until now, said you just have to graph them on our calculators, y1 and y2, and find the point of intersection. So something straightforward, like 3 to the x is equal to 7. That's an exponential equation. So remember, what makes it exponential is that the variable is in the exponent, as opposed to, x to the third would be 7. That's a power equation. And this, we just take the cube root of both sides. But when we get the variable in the exponent, what we're going to do is take the log of both sides. It doesn't really matter. I think there's a way in your calculator you can get to the logarithm base 3, which is fine, but you have right on the front a common log and a natural log. So typically what's done is you use one of those two, and it doesn't make any difference. You get the same answer, whether this is a common log, a logarithm base 10, or a natural log, whichever one of those buttons you have on the front of your calculator. The reason for taking a log of both sides is so we can use that property of logarithms that allows us to bring the exponent out in front. So this is huge because it takes the variable out of an exponent and makes it into an ordinary multiplication. So now what we have is this weird constant, log of 3 times x equals another weird number. But this is really just an algebra 1 problem, right? It's a number times x equals another number. To solve it, you just divide by that number. So you go to log 7 divided by log 3, and then you go to your calculator, and it's just a matter of entering that. And I'll let you do that, and want to give it to me for 3 decimal places? 771?
Yeah.
Okay, okay, sounds like we agreed, because it was like in chorus there. So if we don't already have the exponential completely isolated, because I just gave you that one where the exponential was by itself, then you may have to do some work first to isolate the exponential and then take the log of both sides. So if we have something like 3 times 5 to the, 2 to the 5x minus 4, all in the exponent, plus 7 equals 71. So the exponential is still there, but it's kind of buried inside a bunch of other stuff. So you just have to unbury it. Right? So we have to get rid of all the other stuff, get rid of the 7, get rid of the 3. Then we can take the log of both sides. And then because our exponent has more than just x, we're still going to have to do some more unraveling there. Does that kind of make sense? But don't jump in and take the logarithm right away. That's just going to make a mess of it. So first subtract the 7. So subtracting 7 from 71 is?
64.
Good. And then, now remember, 3 times 2 to this power is not 6 to that power. That's another one of those myths that we have to bust. Because you know the order of operations is you have to do the exponents first before you multiply. So there's no way for that 3 to jump in and be part of the base of the exponent. So you have to divide the 3 over to the other side. And you can do that division. I'm just going to leave it as 64 thirds for now, because I'm going to try to do this with as few entries into the calculator as possible. Now we're ready to take the log of both sides. So we'll take the log of 2 raised to the 5x minus 4 is the log of 64 thirds. Then you can bring that entire exponent out in front. So now we've got 5x minus 4, the quantity, times that log of 2 equals the log of 64 thirds. So then we can divide that log 2 to the other side. So now we have 5x minus 4 equals log 64 thirds divided by the log of 2. And I wouldn't enter any of this into your calculator just yet, but soon, because then we'll add the 4 to the other side. So we have 4 plus this weird log of 64 thirds over log of 2. Then we're going to divide the whole thing by 5. And what I think is easier, you're going to have to put parentheses in here, or if you just go 4 plus, just one calculator entry, 4 plus log 64 thirds divided by log 2, enter, and then divide by 5 after that. That, to me, is the most efficient way to do that on your calculator. Does that make sense? So, and I'd encourage you to kind of do as few calculator entries as you can, rather than doing them all the way along. I think it's harder to retrace your footsteps and find a mistake. So I think I got 1.683. Is anybody else getting that? Okay, so you have confirmation. 1.683 was our answer to that one. Okay, now I'm going to give you another exponential. Any questions on that? We good to go? I'm going to give you another exponential with the difference that the base is going to be Euler's number, E. So because the base is going to be Euler's number, then when we get to that point where we take the log of both sides, it's going to be more efficient to take a natural log of both sides. It'll save us one step along the way there. Not a ton, but at least a little bit. So let's do one like that. So we've got 2 times e to the 1 minus 2x power minus 11 equals 38.
Is that 1 minus 2?
That's 1 minus 2x. You want to do it at the board? Or would you rather have it in your notes? Okay? Your choice.
I don't know, I'm not the crowd.
So we have to get the exponential by itself, add the 11, divide by 2. Now, because here's where it's a little different than the last one, since our base of our exponent is Euler's number e, if we take the natural log of both sides, it just pops out that exponent because these cancel each other out. So we don't, like in the other one, have to divide by the natural log of e because that's just 1. And then you still have to subtract 1 divided by -2, and hopefully we're getting to there. Okay, so far? So let's look at some logarithmic equations and see how we solve those. So for example, I'll start with just a very simple one here, and then we'll work our way up to more complex ones. This is really not any different than what we've been doing. So to solve for x here and get out of the logarithm, what do we need to do? Yeah. So there's 2 ways you can think of this that are mathematically sound. You could think that the base of this logarithm is Euler's number e, and say e to the second equals x, like we do. That's the corresponding exponential equation that's equivalent. You could also, correctly, it seems weird if you haven't done this before, you could think of raising both sides of the equal sign as an exponent base Euler's number, exponentiating both sides. Because now these are going to cancel and just give you the x, and there's your e squared. So if we want the exact answer, this would be fine, because that is the answer. And you can throw it into your calculator.
7.389.
You've got 7.389. Okay? So then we can bury that a little deeper. So if we have 5 plus 2 natural log x equal to 4. Now, like we saw with the exponentials, you have to get the logarithm by itself first, and then get out of that logarithm.
Would you divide by 2?
Eventually, but what do we have to do first?
Subtract.
Yeah, subtract the 5 first. And then, like you said, divide by the 2. And then you can, like we said, there's 2 ways you can think of it. Yeah, and that would be the exact answer. We just leave it as e to the -1/2. Or if you throw it into your calculator,
0.6.
what is it?
0.607.
0.6607. So either of those would be okay. Okay? All right, well, we're working our way up to more complicated ones. Next stage is we're going to get a logarithm equal to a logarithm. So logarithm base 3 of 5x plus 1 is equal to the logarithm base 3 of x plus 7. Now you think about this for a minute, so let's talk about what we can do. Sage, what do you think?
Wouldn't it just be 5x plus 1 plus x plus 7?
Exactly. So the only way 2 logarithms with the same base can be equal to each other is if they're inside, their arguments are equal to each other. So you can just drop the logarithms and set them equal to each other. You could also, like we said, mathematically, you could think of raising both sides as an exponent base 3, which would do that same thing. So that one's not too tough, hopefully. Getting 3 hands. That okay? That all right? Good job.
Maybe 6.4.
Okay, have it your way. That would better?
I have a question. Does
Yeah.
anybody use that giant block of chalk?
Yes,
Oh,
Misha and I use it.
Not enough, because clearly it's still hanging around.
Did you ever tell us the story of the Hagurama? What is it called?
I'll have to see you.
Because I feel like you told me in Katya last year.
Yeah.
All right, here you go, Paige. Have it your way.
Oh my gosh. Thank you.
You're welcome.
Okay, now this is more standard fare for what we get for a logarithmic equation. So, ideas, strategies,
Let Aaron finish writing.
properties of logarithms you may want to employ.
Oh, can you multiply?
Yes, the sum of two logs. Remember, one of our properties was the log of xy is the log of x plus the log of y. So we're gonna go right to left. The sum of two logarithms is the log of the product. Okay, so this is called condensing. We're gonna combine these into a single logarithm on the left side of the equal sign. So we're gonna get to the log of x times x plus 2 is equal to 3. Okay? Now it's more routine. We have a logarithm equal to a number, so to get out of this logarithm, we can do our corresponding exponential, or you could raise both sides as an exponent base 2, if you want to think of it that way. Those are both good ways of conceptualizing it. So we're going to get, if I multiply that out, that's x squared plus 2x is equal to 2 to the third. You with me there? And we know 2 to the third is 8. And to solve a quadratic, we want to make it equal to 0. So we'll subtract that 8 to the other side. Okay, and then we can do our factoring magic. However that magic is done, which is going to be
This is so
plus 4
exhausting.
and minus 2, which means it looks like at first glance there's going to be two solutions, namely -4 and +2. But here's where you got to be careful.
You can't do the log of the negative one.
Right, a logarithm's not defined for a negative or 0. And if you plug a -4 back into either of these, it's not going to be defined. So that's called an extraneous solution. So it solves what we got after we got out of the logarithm, but not where we were before with the logarithm. 2 is okay,
Wait,
so it's going to be our only solution.
could you have done it could you have canceled the logs out with 2 in the first place?
Not until you make it into a single logarithm.
Oh.
So you can't like try to distribute the exponentiating to over that addition. So that won't work.
Alrighty then.
Okay, let's try another.
One more.
One more, I think we can do. So let's do the natural log of x minus 2 plus the natural log of 2x minus 3 is equal to 2 natural log of x.
Hard work.
Oh, yeah. There's another property of logarithms you can use on the right side of the equal sign too. So on the left side, we said we can make this the natural log of their product. Okay.
Yeah.
On the right side, when you have a number times a logarithm, what can you do with that number in front?
Put it
You can bring it into the logarithm as an exponent, right? So we said the log of x to the n is n log x, so we can go right to left as well. So that's going to be the natural log of x squared. Now we have a logarithm equal to a logarithm.
So you could cancel out.
Yeah, drop those logarithms, and we're going to get just the x minus 2 times 2x minus 3 equal to x squared. We're going to have to multiply that all out. So 2x squared looks like a minus 3x, a minus 4x plus 6, still equal to x squared. You can subtract that x squared from that 2x squared, combine the minus 3x and the minus 4x. You are speedy with that big chalk. And then we can factor that.
Imagine how fast I'd be with a little chalk.
Oh my goodness. Here.
Fastest hand in the land.
Alright. So it looks like at first glance, we're getting both 6 and 1, but 1's going to have a problem in both of those. I think 6 is going to be okay. So the 1 gets tossed, and 6 is our only good solution.
I may be fast, but I was also wrong.
Uh-oh.
Uh-oh. You probably
I think
just
you forgot
factored
the
it wrong.
2x. It's 2x minus 3, not
I did 2x minus 3.
plus 3.
Wait a minute, hold on.
2x squared minus 7x